Um, Thank you for the introduction. My research project was part of my undergraduate thesis, and it's called One-Step Bioprinting of Reinforced Multi-Channel Hydrogen Fibers using chaotic advection. Reinforced muscle-like constructs withstand extended cultures in a vacuum bioreactor. So, we have been talking in previous projects about chaotic bioprinting, which is a novel technique that allows us to obtain hydrogel fibers at high throughput in a single step and in an economic fashion. And we can print two or more materials at the same time, so they mix together and we can obtain one predictable pattern and one fiber of 1 millimeter of diameter with different layers of material. So in recent reports of Bolivar, Ceballos and co-workers, they could adapt this technique to co-extrude two materials, one permanent material and one fugitive material. So they could obtain hollow fibers that resemble the vascularization inside one native tissue. And they could obtain up to 32 microchannels inside the construct. However, this technique still faces some limitations. For example, the hollow fibers do not have good mechanical properties and they cannot withstand extended cultures of time, and it's important that we can have an extended culture because in this way we can obtain finally mature tissue. So in that sense, my project was based on optimizing chaotic bioprinting, but instead of using one kinetics of 2 inlets, we use 8 entrances. So each color that we can see in the picture represents one inlet, and we can see a simulation of one cross-section of the fiber, and we can see how the different materials can be intercalated in one single structure. And also we use two mixing elements, and when we co-extruded the fiber through the nozzle, we did one cross-linking of permanent materials such as alginate and calcium chloride, and after that also the sacrificial material can dissolve. Then we use photo cross-linking with UV light for reticulating gelma with alginate, and finally we can obtain one multi-material fiber that has hollow microchannels inside it. So we can see in this picture, in the bright field, we just printed one fiber with gelma and hydroxytyl cellulose, and alginate and hydroxytyl cellulose. In alginate, we put red microparticles, and we could see in the fluorescent microscope, and so we can observe that how the microchannels were formed, because in the bright part inside the fiber that represents the hollow, the light could pass through. And the other material that is the permanent material was alginate as a proof of concept. So after that we wanted to print one multi-material fiber, so we used 3 materials: alginate as one super material to improve the mechanical properties, hydroxytyl cellulose as one sacrificial material, and gelma alginate as a bioink that was loaded with cells. We have 3 materials, but we have 8 entrances, so we can have different combinations and we can have different composition inside our fiber. But as our main problem was the mechanical stability, we wanted to improve the mechanical properties, and for that reason we wanted to optimize the proportion of alginate that we have inside the fiber. And we can change the number of inlets where we put the alginate. So we have conceptual cross-sections that was obtained by CFD simulations, and also experimental cross-sections, and we can see how when we vary the proportion of each ink, the patterns preserve in the cross-section and are similar to the ones that we can see in the simulation. So we know that we can obtain predictable patterns inside our structure. And also we characterize the proportion of each ink in terms of the percentage of area. And we can also observe that the conceptual and experimental proportions of each inks are similar together. So then we optimize the mechanical properties, and for that reason we do tensile assays and varying the number of inlets with alginate. and we obtained a stress-strain curve. With this curve in the linear section, we could obtain the elastic modulus, and so we observed that the fibers that were made just by alginate had a higher elastic modulus, and then we find an optimal point between 3 of 8 inlets with alginate and 4 out of 8 inlets of alginate. However, as we remember, the alginate is just one structural material and doesn't contain cells. So for that reason, we also wanted to put as much layers with cells as possible. So in that sense, we prefer to work with one fiber with 3 out of 8 entrances of alginate as one fiber with optimal mechanical properties. And then once we optimize the mechanical properties, we move to the cell culture, and we loaded C2, C12 cells because they are mouse myoblasts, and we wanted to use this technique to, in the future, could obtain mature skeletal muscle tissue. So the fiber, which had the optimal mechanical properties, was loaded with C2, C12 cells in the Gelma alginate ink, and we used one solid fiber as a control that doesn't contain any hollow microchannels and was just made by one entrance of a high viscosity alginate and another entrance of Gelma with the same cell line. And in both cases, we can obtain one fiber with 16 layers. The differences is that one has hollows and holes, and the other doesn't have holes. So we also compare two culture methods: a static culture, that's traditional culture in one incubator, and the agitation culture in a rocking bioreactor that was made of one agitation system and one hidden system made in Arduino. And we put the chaotically bioprinted fiber inside one T25 flask that was continuously agitated. So first we do the light-death assays to characterize the cell viability of the cells. And first we see that we did it for solid and hollow fibers at days 1, 7, and day 14. And we can observe that how the cell viability improves when we use hollow fibers. Also, we did the same analysis for the fibers in the agitation for day 1 and day 7 for both solid and hollow fibers. And we can observe clearly in these images that the agitation improves the cell density. I mean with this, the amount of cells that grow inside the construct for both solid and hollow fibers, and also had a higher cell viability. We can see in these two videos a comparison of solid and hollow fibers at day 7 with agitation in the rocking bioreactor. So the first video was about one solid fiber, and the second video about hollow fibers, and we can observe that both of them have a high cell viability. I mean by this, a high amount of cells stained by a green fluorescent. Okay, so we also wanted to quantify these results. So we did one image processing to obtain the percentage of light on the cells. So we can observe that in hollow fibers, in static, they had a higher cell viability, and this also shows in the agitation process. But the differences is that in agitation processes between solid and hollow fibers, we could not observe so much differences. But we can see that between day 1 and between day 7, the cell viability improves in both cases. And also we did actin DAPI staining for solid and hollow fibers at day 14 in static agitation. So we can see in solid fibers how the cells just grow in the surface and they form a thin layer. Meanwhile, in the hollow fibers, we can observe that they can grow more deep inside the structure, forming one wall around the fiber. So this means that even if we have the same amount of layers inside one structure, if we add hollow microchannels inside it, we can improve how the cells can spread and grow in the construct and not only remain in the surface. This is due to a better mass transfer of nutrients. And finally, we assess the cell density of the cells. We can see in solid and hollow fibers in agitation at day 7. So we can observe that in both cases they had a high cell density, but we wanted to quantify this better in using image processing. So we obtained this graphic, and we can observe that we have higher cell density when we use agitation compared when we use static cell culturing. So this means that our putting the cells in our bioreactor improve cell density. And also we can observe that between solid and hollow fibers, when they are in agitation, we couldn't see so much differences, but we have to do further research to see why this is happening, because we expect that hollows will improve even more the mass transfer of nutrients. So finally, this is significant because we can transfer 3D bioprinting from the micro scale to the macro scale, and this can be used in the healthcare industry, in academia to improve knowledge. And finally, we want patients to benefit from this type of technology. So I want to say thank you to all the Alvarez Trujillo lab members from Tecnológico de Monterrey and Universidad de Ingeniería y Tecnología from Lima, Peru, and everyone who helped me through this project. And so thank you so much, and I'm open for your questions.
Thank you, Andrea, for your wonderful presentation. Are there any questions? Yes.
Hi, Andrea. Thank you for your presentation. So I have a question. I wonder, when you were showing the life and death experiments, you showed that the fiber that was in agitation just you reached the experiment until day 7. So why you didn't show the day 14? Because in static you have day 14. So I'm just wondering why you don't make that comparison.
Thank you for your question. Well, due to time constraints, we could just obtain results for day 7 in agitation. But we expect that in the future, when we continue with this project, to characterize the fibers until day 14, because we could observe that they can resist until day 14 in agitation, but we didn't do the analysis of light death or other stainings. So that's why I didn't show it in this presentation. But if we have more time, we can reach to this point.
Any other question? I have a quick question. You mentioned the viability, but I was wondering also the stability of the material. Have you noticed any differences between the solid one and the hollow one on how the material persisted through time?
Thank you for your question. Yes, there's differences in the degradation of the material. We assessed in other set of experiments the degradation over time, and we can observe that in both cases the material degrades, even if it's a solid fiber or hollow fiber. But we need further research and further experiments to see in how is the differences between the both of them, and to do one statistical analysis so we can know accurately if it's significant or not. But just by looking at the bright field in a microscope, we could observe how, passing the days, the fibers start degrading in the walls due to agitation, which did not happen when we did a static culture.
Thank you very much, Andrea. Can we give her another applause?